Now, good morning, everyone. Let us now start improving the transient response via the cascade compensation. Previously, it was the steady state response. Now, we will discuss the transient response. Since we have solved the problem of improving the steady state error without affecting the transient response, now let us now improve the transient response itself. In this module, we will discuss about the two methods of the transient improvement of the transient response based on the cascade compensation. Now, the main objective to design a response that has the main objective to design a response that has desirable percentage overshoot, and shorter settling time. So settling time should be less and percentage overshoot should be desirable. So this is the objective of this improvement in transient response. Now, the first technique that we discussed, it is the ideal derivative compensation. With ideal derivative compensation, a pure differentiator is added. To the forward path of the feedback control system, and we will see that the result of adding the differentiation is the addition of 0 to the forward path transfer function. This type of compensation requires an active network for its realization. So active network is required for its realization. Further, the differentiation in this case, the differentiator that we use in this case is noisy process. Although the level of the noise is low, the frequency of noise is high compared to the signal. Thus, differentiating high frequency noise yields a large unwanted signal in this technique. Now, the second technique does not use the pure differentiation. Instead, it approximates the differentiation with a passive network by adding a 0 and a more distant pole to the forward path transfer function. The 0 approximates pure differentiation as we have described previously. So we call this first compensator as the proportional plus derivative controller. That is, the first one is the proportional plus derivative plus derivative controller. The first one is known as the proportional plus derivative controller, and it can be realized with an active network. Now, it is called so since its implementation consists of feeding the error. Its implementation consists of feeding the error proportional plus derivative of the error. Proportional plus derivative of the error to the plant. The second technique uses a passive network, and this is known as the lead compensator. The second is known as the lead compensator. It uses the passive network. It is known as the lead compensator. And previously that we have discussed the lag compensator in case of steady state response. So it is the lead compensator, and its name is due to the frequency response that we discussed in the frequency response chapter. Now we use the name proportional plus derivative controller, which is also known as the PD controller. Proportional plus derivative controller with the ideal derivative controller. So as in the previous case, it is also known as the ideal derivative. It is also called the ideal derivative controller. So proportional derivative plus derivative controller or the ideal derivative controller. And we use the name as the lead compensator when the cascade compensator does not employ the pair differentiation as in this case. Now come to the ideal derivative compensation. Now we see that transient response of a system can be selected by choosing the appropriate closed loop pole location. By choosing the appropriate closed loop pole location on S-plane. And if this point is on the root locus, if this point is on the root locus, then simple gain adjustment is all that is required to meet the transient response specifications. To meet the transient response specifications. Now, if the closed loop pole is not on the root locus, let us suppose that this is the root locus and this closed loop pole is not on the root locus, then the root locus must be reshaped. It must be reshaped so that the compensator or the new locus must go through the selected closed loop pole location. So, if it is not on the root locus, then we must reshape that locus in such a way so that this pole must lie on the root locus. Now, in order to accomplish this, poles and zeros, in order to accomplish this, the poles and zeros must be added in the forward path to produce a new open loop function whose root locus will go through the pole, through the design point in the S-plane. Now, one way is to add a single zero to the forward path. That is, one way to do it is to add a single zero in the forward path, and this single zero is represented by this zero can be represented by a compensator whose transfer function is given by S plus ZC. Now, this function, the sum of the differentiator and the pure gain, is known as the ideal derivative controller, or it is known as the proportional plus derivative controller, or the P.D. controller. Now what is the importance of that? That its judicious choice that is the choice of the compensator 0 can quicken the response as compared to the uncompensated case. So its judicious choice can quicken the response as compared to the compensated case. Second, the transient response unattainable, by simple gain adjustment, can be obtained by augmenting the system poles and the zeros with an ideal derivative compensator. So the response which is unattainable by this gain adjustment can be obtained by using pole and zeros, and along with the pole and zeros, the ideal derivative compensator, that is this one. Ideal derivative compensator, it will speed up the response of the system. It will speed up the response of the system. Now let us discuss some examples. Now let us consider a system. This is the uncompensated system. Let us consider the system, uncompensated system, and this is the compensated system where the 0 is placed at -2 and -3 and the -4. So this is the uncompensated system, and in the compensated system the zeros are placed at -2, -3 and -4. Now we will see that there is the different root locus in each case. For each compensated case, the dominant second order poles, that is the dominant second order poles in this case, the dominant second order poles are away along the 0.4 damping ratio than the uncompensated case. So first it was here, now it is here, now then in this case it is here and it is here, that is dominant second order poles are far away. Also each of the compensated cases has dominant pole with the same damping ratio in this case. Though damping ratio is same in this case, and as a result, since the percent overshoot is proportional to the damping ratio xi, so it is percent overshoot is same in all the cases. So percent overshoot is proportional to damping ratio. So as the damping ratio is same in all the cases, so does the percent overshoot. Also the compensated dominant closed loop poles, that is compensated dominant closed loop poles, this one and this one, has more negative real parts than the uncompensated part, this one, then uncompensated dominant closed loop poles. So as the settling time is inversely proportional to this real part, so we can see that the settling time for the compensator is reduced. So the settling time for the case where the compensation is used is shorter or is reduced as compared to the uncompensated, as compared to this uncompensated case. So it has the compensated cases has the closed loop poles which is on more negative part, and as a result have shorter settling time, as this settling time is inversely proportional to this real part. Now also one more observation, that all the compensated system will have the small value of the peak time. It will have the small peak time than the uncompensated system, since the imaginary part of the compensated system is larger as compared to the uncompensated system. So settling time is less and peak time is also less because of the real part, and this because of the imaginary part. So these systems P, C and D has smaller peak times. Now all the parameters are in all the cases are shown here. That is, first one is the uncompensated case, then we have the compensation B, we have the 0 at s equals to -2, then 0 at s equals to -3, then 0 at s equals to -4. So we also notice that as the 0 is placed further from the dominant pole, the compensated dominant poles, the closed loop compensated dominant poles moves closer to the origin. That is, this, as it moves further, the compensated dominant poles moves closer to the origin. So this observation can also be made. These are the values: xi, omega n, then percent overshoot. Percent overshoot in this case remain constant because xi damping ratio is constant in this case. It depends upon that. Then settling time is also reduced in this case. Then we have the peak time, it is also reduced in this case. Then we have Kp is also increased, and error is reduced in this case. Error is also reduced in this case. So third pole, value of third pole here, this one and this one, then 0, and then whether the second order approximation is okay or not in this case. From this table it is observed that although the methods in this C and D yield the slower response than the method B, however the addition of the ideal derivative compensation shortened the response time in each case while keeping the percent overshoot constant. That is, response time is reduced, however the percent overshoot is constant. Now this change can be seen in terms of the settling time and the peak time, where there is at least a doubling effect in this case, settling time and the peak time. So there is at least a doubling of speed across all the cases of compensation. Now the benefit of this improvement is that the steady state error has been reduced in this case. Even though we are using this compensation, the steady state error has been reduced, though we are not concerned about the steady state, but still the steady state error in this case is reduced. And here we can say that the steady state error is reduced to about 1/3 of this uncompensated case. Okay, and time responses for all the systems is also given here. It is the uncompensated case. Here we have the 0 at -2, then 0 at -3 and 0 at -4, and we see the compensated responses are faster and exhibit less error as compared to the uncompensated case. So once we have decided the location of the compensating zero by using the design, then we have to implement this PD controller. This, as we have done in proportional plus integral controller, the ideal derivative compensator used to improve the transient response is implemented with the proportional plus derivative controller, that is the PD controller. For example, let us consider this case, and the transfer function of this is the controller, and the transfer function of this is given by K2 into S plus K1 divided by K2, and K1 by K2 is chosen to equal the negative of the compensator 0, and K2 is chosen to contribute to the required loop gain value. So in this case, this K1 divided by K2 is chosen to equal to negative of the compensator 0 that we added in the compensator, negative of the compensator 0, that is 0 that we have to add, and K2 in this case is actually to contribute to the required loop gain. So this is the function of K1 and K2 in this case. Now, so this ideal derivative compensator, it can improve the transient response of the system. It can improve the transient response of the system. However, it has some drawback also. First one is, drawbacks are the disadvantages. First one is that it requires the active circuit to perform the differentiation. Active circuit is required for differentiation. Second drawback is that differentiation is actually a noisy process. Differentiation is a noisy process. However, the level of the noise is low. Level of the noise is low, but the frequency of but high frequencies can lead to large or unwanted signals. High frequency can lead to large unwanted signals, or saturation of amplifiers or other components. However, after this we will discuss the lead compensator, which is actually a passive network used to overcome the differentiation of overcome the disadvantage of ideal differentiation and still retain the ability to improve the transient response. That lead compensator we can discuss in the next module. Now let us take an example of ideal derivative compensator design. Now given the system shown in the figure, design an ideal derivative compensator to yield a 16% overshoot with a 3-fold reduction in the settling time. This is this feedback control system. Now in this case the overshoot is 16%. We have the 16% overshoot in this case. Percent overshoot in this case is 16%. Now the root locus of this system is drawn here. We have this system having 3 poles and no zeros in this case, so the root locus is drawn here in this case. Now with this percent overshoot, since the damping ratio is dependent on the percent overshoot, so damping ratio, by using the expression for the damping ratio and percent overshoot, the damping ratio is found out to be 0.504 in this case. Now as we have done in the previous case, to search the dominant poles, closed loop poles, we search along this line of this damping ratio. Where this damping ratio gives the value of 1, it is on, then we can say that this is on this axis, that this point lies on the axis. So we search along the damping ratio line for an odd multiple of 180 degree and find the dominant second order pole. The dominant second order pole will found out to be minus 1.205 plus j 0.026 at k equal to 43.40 at k equals to 43.35, that is gain k in this case. Now from this imaginary part we can find the and damping ratio, we can find the settling time. So settling time is found out to be 3.320. Now this formula is formula for the second order approximation. Now we have to see whether our evaluation of percent overshoot and this settling time is based on the second order approximation, as whether it is justified or not. So beyond 6, that is this pole, we have to find the on the real axis for a pole whose gain is equals to k equals to 43.45, and we find this third pole at minus 7.59. So since it is over 6 times than this, it is over 6 times than this one, so we can say that our approximation is valid. Now we proceed to compensate the system. First we find the location of the compensated system dominant poles. So in order to have the threefold reduction in the settling time, so that situation is given, that we have the threefold reduction in the settling time, and settling time that we have calculated. So the new settling time calculated, we have 3 times reduction in the settling time, and new sigma real part of the compensated system dominant second order pole is equals to 3.613. So it is the real part of the dominant second order pole, and the imaginary part can be calculated by this formula. Imaginary part can be calculated by this formula. It is found out to be 6.193. So these second order dominant desired compensated dominant poles are shown on this line as this, and this is the root locus. This is the uncompensated system dominant pole, and this is the desired compensated dominant poles. Now we have to design the location of the compensator 0. We get the compensated dominant poles Now we have to know about the compensated 0, that is location of the compensated 0. In this case, what we do, the result is the sum of the angles to design point of all the poles and the zeros. As we have discussed in the previous case, the result is the sum of angles to the design points from all the poles and the zeros. All the poles and the zeros to the design point. So design point in this case is this. Now, so of the compensated system, and so we are only left with 1 0 from which we want to get the value of the angle. So difference between the result obtained and 180, since all the sum of this is equals to 180 degree, so difference between whatever result we get minus 180 degree will give the angular contribution of the compensator 0. This contribution of compensator 0. Now, using this, we found the angle to be minus 275, and the angular contribution required for the compensator 0 for a test point on the root locus is equals to 275 divided by minus 180 degree, which is equals to 95.6 degree. Now, that is this 95.6 degree. So we know this angle, we know this dominant, we have to find the value of this sigma in this case, and by using the relation in this case, the sigma is found out to be 3.006, and the complete root locus of the system is given in this figure. Complete root locus of the system is given in this figure. So this is the root locus for the compensated system. Now, so all the parameters for an uncompensated and compensated system are shown here. Now these are the dominant poles, the value of the gain k, then we have value of xi, then omega, and then percent overshoot in this case. Then we have value of tp, ts, kv, and then error in this case, third pole. Now from this, so however, for an uncompensated system, the estimate of the transient response is accurate, since the third pole in that uncompensated system is 5 times the real part of the dominant second order pair. However, the second order approximation cannot be valid in the compensated system. It may be invalid because there is no approximate closed loop third pole, and because there is no approximate closed loop third pole and zero cancellation, closed loop pole and zero cancellation, so this pole 0 is not cancelling, so the second order approximation cannot be used in this case. And the final, for a compensated and uncompensated system, the final result is shown here, that is, this is for the uncompensated system and this is for the compensated system, and which shows that the compensated system is faster in response as compared to the uncompensated system. So this is all about the design part. Thank you very much.